Good day, my name is Chitalu Jamnda. I'm one of the engineering students at the University of South Africa. Today my presentation will be about alternative electrical infrastructure design of a rural hospital in Qwaqws. Climate change is driving the global shift towards sustainable energy solution. Iceland, a country with nearly 100% of electricity consumption coming from renewable sources, has been actively involved in offering geothermal technical assistance and renewable energy education. The country has participated in geothermal projects in over 50 countries, including the construction of the world's largest geothermal district heating systems in China. South Africa has made a significant progress in concentrating solar panels (CSP) industry, with 6 plants with a total installed capacity of over 500 megawatts. The country aims to generate over 1.7 gigawatts of renewable energy by 2030, leveraging its solar energy potential. The South African government solar water program has led to the installation of over 410,000 solar water heaters, accelerating the growth of solar water industry. The Sishen Solar Power Plant, one of the largest solar farms in the continent, spans over 250 hectares and is owned by consortium including Asuna Royal Bafokeng Holdings, Seoul City, the Bang Community Solar Energy Trust. The plant has created 19 permanent jobs and generated electricity that can power up 100,000 homes. The aim of the project is to provide an alternative electrical infrastructure design for rural hospital in Qwaqws, which is located at Ngaka Modimo Molemo District Municipality in the Northwest Province of South Africa. The purpose is to ensure that patients have continuous access to critical medical services, even in the event of power outages and infrastructure constraints. This design aims to offer dependable and sustainable electrical power solutions that may handle the particular issues faced by healthcare facilities in distant places. The project has the following objectives. Objective 1, to provide a full electrical layout for the hospital building. The requirement is to use a software to draw out the layout. Objective 2, to complete a single line diagram of the entire installation from the source transformer to the final loads. It is also a requirement to use a software to draw up and simulate the single line diagrams. The following is to be considered with respect to the various aspects of the electrical design: the installation method of the conductors, the choice of conductor size based on the load requirements, the voltage drop across the conductors, utilization factor. Literature review. In Nigeria, access to modern electricity is limited, particularly in rural communities where over 70% lack access. This has led to biomass being the primary source of energy, resulting in the lack of power generation capacity. A study emphasized the need for energy solutions to operate primary health centers in rural communities. The study used Abadama in Nigeria as a case study and conducted an electrical, economical, and environmental analysis to plan localized energy supply for rural medical services. The research conducted a thorough analysis performance matrix criteria in designing and planning a standalone PV energy supply system. The study highlighted the importance of these metrics in ensuring the long-term reliability and sustainability of standalone PV supply systems. The findings provided valuable insight into the design and planning consideration for standalone PV systems, which can greatly benefit remote applications that lack access to traditional power grids. This is the daily radiance graph that spans from January to December. We can see the clearness index, the maximum clearness index is we get the clearness index at mid-June. Then our lowest point is during our December time. An innovative solution to meet the electrical energy demands of a health clinic in South Africa was explored, involving an off-grid renewable energy systems that combine solar PV and wind turbines with hydrogen storage scheme. The project required a 40 kilowatt solar PV system, 3.10 kilowatt wind turbines, 8.6 kilowatt fuel cell, 25 kilowatt electrolyzer, and 40 kg hydrogen tank capacity. The total capital cost of the microgrid was found to be $177,600 with the net present cost of $260,323. This is the block diagram that was proposed. So we see we've got our H2 tank, then we have our AC and DC. On our AC side, we've got our fuel cell, the grid, wind turbines. Our DC, we've got our electrolyzer as well as our PV panels. Then we've got our alternator, our converter in the middle. The total peak wattage that is needed is 7.6 kilowatt. Future research should focus on investigating the dynamic models and fuel cell electrolyzers integration into power systems, which includes intermittent renewable energy generators. To analyze the impact of intermittency on the voltage stability of fuel cells. A block diagram of the proposed photovoltaic system. We've got our solar module or array. I've got our overcurrent protection, which can be our fuse or our circuit breakers. Then we have our charge regulator, which then can feed to our DC loads, or it can feed to our battery storage. Then from our battery storage, we can have fuses that will protect our inverter. Then our DC voltage is converted to AC to supply our AC loads. 3 on low voltage installation. SANS 10142-1 edition 3.1 defines low voltage installation as circuits supplied at a nominal voltage of up to 1000 volts AC or 1500 volts DC with a standard frequency of 50 Hz. It also includes circuits operating at a voltage exceeding 1000 volts derived from an installation with a voltage not exceeding 1000 volts AC. Wiring systems and cables not specifically covered by the applicable standards. Consumers installation external to buildings. Fixed wiring in power supply circuits for telecommunication equipment. Signaling equipment and control equipment, extension or alterations of installations, fixed wiring of complex machineries equipment for which no standard is referred to, compound replacement or maintenance and earthing arrangements. This is the electrical layout plan that is part of the report. This is where you'll find all the arrangements. This is where you'll find all the features that are included in the design, which is then transferred to the single line diagrams. This is our single line diagram. We've got our protection circuit breakers. We've got circuit breakers as protection. We've got each leg is representing a particular load that is being fed from the system. Voltage drop. To obtain the voltage drop at 5%, we use the voltage of the solar modules, which is 24 volts. So the voltage drop that is allowed in the system is 1.2 volts. And this is applicable to all the cable calculations throughout the report. This is the required power calculations that were used when designing the system. We can make an example with two. The smoke detector takes 0.050 amperage. Then our nominal voltage is 230, the quantity is 15. So the wattage of the smoke detector is 172.5 watts. We times that by the hours in a day, of which it's used 12 hours. We times it by the amount of days that is being used in a week, which is 7 days in a week. We times it by 7, which is 7 days. We get 2070 watts hour. Make an example of another one. The water pump. Water pump, the quantity that we're going to be using is 1. The nominal voltage is 230. We take that, we times it together. We get an amperage of 0.460. Then we times the current as well as the voltage. We get a watts value of 105.8. We times that by the amount of hours that is being used per day, which is 6. Times it by the used days in a week, which is 6. We times it by the amount of days in a week. Then the answer thereof is 544.11 watts hour. So all the appliances, the equipments that are going to be used in the hospitals are marked and labeled and calculated using these formulas that we just discussed now. The total watt hour is 22,385 watt hour. Calculating of power rating of components. We need to know and we need to calculate the solar panel size, the battery capacity, the inverter capacity, the fuse or the circuit breaker that is going to be used for protection. Solar panel sizing. We will need the total kilowatt of the system and the average solar radiance of the area in question. Using the lowest of the average, we use 5.5. Solar reductance is 5.5. The required power is 22,385 watts hour, which is 22.385 kilowatt hour. Therefore, we use the formula solar power wattage required, which is required power over solar radiance. So it's going to be 22.385 kilowatt hour divided by 5.5, which the answer thereof is 4.05 kilowatt hour. Selecting a 300 watt solar panel will be convenient for the application. So we say the number of solar panels that we are going to need for the system is solar power wattage over solar panel power, which is 4,070 watt hour divided by 300 watts, which will get 14 panels are going to be needed. Therefore, we also understand that there are losses, and panel systems losses can range up to 25%. Therefore, we need to increase the number of panels by at least 25%. The number of panels to account for the losses will equals to 14 plus 14 times 0.25, which equals to 20 panels of 300 watts each. Battery capacity. Battery energy storage capacity depends on the length of time you want the battery to supply your home and your energy consumption. Considering your daily energy consumption of 22.385 kilowatt, a depth discharge of 80% using lithium, and a desired autonomy of 7 days, you can calculate the required battery capacity as followed. Battery capacity in watts hour, which is 22,385 watts hour, you divided that by 0.8 times 7 days. The answer therefore is 3,907 watts hour. Quantity, we say the battery capacity divided by the battery voltage, which is 3,997 divided by 24 volts of the batteries, which gives us an answer of 167. Therefore, the battery capacity needed is 167. Inverter capacity. To size a solar inverter, first we determine the total power output of the solar array by calculating the efficiency of the inverter. The solar inverter with a rating above 95% is ideal for a maximum efficiency. However, the system loses like temperature effect, voltage drops, and accumulation can reduce the overall efficiency. To account for these losses, we multiply the total output by a derating factor between 0.85 and 0.9. The required capacity of the inverter can be calculated based on the derated power output, adding a safety margin of 10 to 25% to account for uncertainties. In this case, the inverter capacity will be obtained by power multiplication with the derating factor 22.385 kilowatt by 0.85, which will give us 19.027 kilowatt hour. Power multiplication with the safety margin, which is 19.027 kilowatt hour by 1.25, which will give us an answer of 24 kilowatt hour. Therefore, the inverter size should be at least or should be 24 kilowatt. Fuse or circuit breaker. To account for potential surge and fuse, a fuse is installed as a protection device. Fuse sizing 29 amps by 125, which gives us 36.25. The next standard size fuse or circuit breaker would be 40 amp. If a disconnector is needed, a 60 amp fuse or non-fuse disconnector is recommended. Connecting the inverter output to a 40 amp breaker is crucial for wiring protection. Component selection. These are the components that we have chose with their particular spec. So the first component is an inverter. The second component would be our battery with their spec. The circuit breaker size, which we've already discussed, which is 40 amp. Component quantity and prices. This table indicates to us the quantity, the price, and the total thereof of the whole system. So the solar panels will cost 85,986.9 rand. The inverter will cost 20,000. The batteries will cost 6,606.19 rand. Breaker will cost 1,000 rand. The fuse will cost 1,000 rand. So the total amount for the whole system will be 6,714,002 rand 90 cents. In conclusion, the Huma software models is a valuable tool for determining the most economical solar systems for remote health clinics. It simplifies the process of considering factors like clinic location, energy requirements, and available resources. The model ensures a solar system that meets the hospital energy needs while minimizing cost. Future research should use Homa model for electrification of rural hospitals, as many in developing countries lack reliable electricity, negatively impacting healthcare services. By using the model, rural hospitals can improve their energy access, leading to a better patient outcome. We've come to an end of my presentation. Thank you for giving me the opportunity, and thank you for listening.